So we will look into some exercises in the coming modules. What we will start with is a very simple exercise dealing with Laplace equation. So Laplace equation is something that you will come across in every part of the electromagnetic lectures as a fundamental equation that deals with potential and how the potential is distributed given certain boundary conditions. So to understand any differencing method, it is good to start with Laplace equation as a starting point and then extend it to Poisson equation, which is having certain right hand side term. So we will explain this while we do the problem. So let us look into the basic equation of Laplace. So what we have is, we have the del square phi is equal to 0 and we have certain boundary conditions given. So let us define our domain. Our domain is going to be a square with points 0, 0, 10, 0, 10, 10 and 0, 10. Again I am just defining it for simplicity. You can define different domain dimensions. It need not be a square, it can also be a circle. So for the simple case, let us start with a square domain and we are going to define certain boundary conditions. So boundary conditions, as we discussed before, are going to be the definition of potential along these four sides. So if we say the potential along these four sides are given by certain value, let us say we are going to give potential on this particular boundary to be 10 and the potential on this side is going to be 0, so phi equal to 0, and the potential on this side is also 0, the potential on this side is also 0. So let us take a very simple example. We see that the potential is going from 10 to 0 and it has to have certain behavior. Physically we can understand that it is going to be a linear drop from 10 to 0 and let us see how numerically it behaves. So for that we have to start with this particular equation and we have to find a difference analog of this continuous del square. So what we have learned in the earlier modules is we can basically use central differencing method. So this particular case we can write them as dou square phi by dou x square plus dou square phi by dou y square is going to be equal to 0. So we have the basic equation in the continuous form written as dou square phi by dou x square plus dou square phi by dou y square equal to 0. What we know from the earlier lectures on finite differencing method, we can approximate the term dou square phi by dou x square using the central differencing method as phi of I plus 1 comma j minus 2 phi of I comma j plus phi of I minus 1 comma j divided by del x square. So what we are doing here is we are doing the central differencing and we are getting the value in this form. Again this is only approximately equal to, you have certain truncation errors. And what we can do similarly is also the other part of the equation, which is this one. So we can write it approximately equal to phi of I comma j plus 1 minus 2 phi I comma j plus phi I comma j minus 1 divided by del y square. So this is del x square and we have del y square, and putting this together what we will get is the 5-point differencing method, where we are using the stencil to compute the value at I comma j based on neighboring points. So we can write them in this form. So if this is I comma j, this is going to be I plus 1 comma j, this is going to be I comma j minus 1, this is going to be I comma j plus 1, this is going to be I minus 1 comma j, and we are computing the value at the center based on certain values at the neighboring points. So this is what we are going to do in this exercise. We are going to use this 5-point differencing method to take the Laplace equation from the continuous space to the finite difference space. So let us look into the code itself and let us see how the Matlab program can be used for simply solving this problem. So let us start with the basic Matlab program. So now let us look into the code itself. So we are setting certain specifications. So these are the specifications which we will use to set the dimensions and the parameters of the problem. So the first one is the Lx, which is the length in x direction, and the second one is Ly, which is the length in y direction, which is very similar to the problem what we have in the paper, as you can see. So the length here in x direction is 10, the length in y direction is also 10, and that is what we have set here, and Nx and Ny are going to be the number of steps in x and y direction. So we have 60 steps in x, 60 steps in y, and the number of iterations are going to be given by n eta, and as you can see I have given here 1 wantedly. The reason is 1 will be a very crude approximation, and we will see how we have to increase and why we have to increase to get better resolution. And dx is going to be the width of the step in x and y direction will be dy. So dx and dy are correspondingly the width of the steps or stepping size in x and y direction, and the value of various x component and y component are given by the x and y parameters, and they are going to go from 0 to Lx with a step size of dx in the direction of x. Similarly they are going to go from 0 to Ly with step size dy in the direction of y. So now we are initializing certain parameters. For example, potential is given by P here, we are pre-allocating them to be 0, and Pn is also a variable we are going to use, and we are pre-allocating it to 0, and we are going to go into the iteration, the one which I explained you in the paper. So we see that we are going to use a 5-point central differencing scheme which I explained to you just now in the paper. We are going to go with certain index which is I for the x coordinate and j for the y coordinate, and the iteration is going to be the for loop, and it goes from 1 to number of iteration. In our case initially we have chosen n iter is equal to 1, and we will see that it is not going to give us good result, but still we will start with that. And now we are using the central differencing scheme I just explained on the paper to compute Pij using the points surrounding it, and we are going to use the 5 points for that. So basically we are taking the 4 neighboring points to compute the value at the center point, that is why we are calling them 5-point difference, and we have set the boundary conditions as given here. So we have set P of dash comma 1 equal to 10. So what I say dash comma 1 is it is going to be for all x coordinate but with one y coordinate. The one y coordinate is going to be y equal to 1, so it is going to be a line that is going to be at y equal to 1. So y equal to 1 will be the first coordinate which we have given here. So this is going to be the first y coordinate, and similarly this is going to be the last y coordinate which is going to be ny. So let us write it down. So this is going to be the phi of comma 1, and this is going to be the phi of comma nx. Similarly, we can write them also for the other two sides. So this is going to be the phi of ny comma dash, and similarly this is going to be the phi of 1 comma dash. So that is what we have done here. So if you see the equation, we have put for the first y line as equal to 10. So this is going to be the line that is going at y equal to 0. So y equal to 0 will be the first coordinate, since we are in the loop going from the value, we are setting the value of I comma j, but we are not worried about the first coordinates because we are setting the value of the boundary conditions. Since the boundary conditions are going to be the first coordinate or the last coordinate, our loop is only going from in between values. So the first value and the last value are actually the boundary coordinates which we are considering here. If you may be wondering why we start from 2 to nx minus 1 or 2 to ny minus 1, the reason is here in the boundary coordinates. So let us run this program. What we are going to plot is the value of the potential phi as a function of x comma y, and we are going to see it in the top view, and we can rotate it and see also in the other views. So once you run it, you see that the potential on the left hand side, I can rotate it. So this is the top view, we are in the xy plane. So if you view it from xz plane, you will see it is showing that the potential is 10 on the left hand side, but the other potential immediately drops to 0, which is not physical. What we expect theoretically is a kind of equipotential lines, and we will see where the equipotential lines are by simulating the problem for more iteration. So let us go and iterate it for, let us say, 100 iterations. So I am putting iteration is equal to 100, and I am running it, and you see that since this boundary and this boundary is also at 0, we will see a kind of a equipotential line. And let us see running it for longer time, let us say I am running it for 1000 iterations. I am seeing that it is replicating, but still I can see the equipotential lines. If I zoom it out, you will see the equipotential lines seen as those different shades of colors, and if we rotate it in a different plane, you will start to see a drop that is happening. So now if we run this same thing for more number of iterations, let us say we run it for 10,000 iterations, which should be good enough. Now we can see the quality of result is improving, and we are able to see a drop which is as we expect. So this is Laplace equation for this particular case. What we can try doing is, we can try changing the boundary conditions in order to see what will be the influence of the boundary conditions for this particular problem. So what I am going to do is, instead of choosing 0 on other sides, I am going to choose certain values. For example, let us say my two edges. So for y equal to 0 and y equal to 10, which is these two edges, I am going to put the value as 10, and the other two I keep it as 0, and I am going to run it for 10,000 iteration steps, and when I do that, I start to see a nice curve of the equipotential lines. What we see is the potential lines are following certain pattern, and you will see that pattern here. So the value here is set to 10, the value here is set to 10, whereas the value on these two boundaries are set to 0, and you see a nice manifold of the potential, and you see the equipotential surface when you see it from the top view. So these are the equipotential surface, and so this is a very good example for you to start with, because this gives us certain understanding of how a simple equation like Laplace equation can be simulated using Matlab and using certain central differencing scheme which we learnt in the previous modules. And this is going to be a very important exercise for you, because we are going to build on this exercise in the next step using Poisson equation, and Poisson equation will be same as Laplace equation except for the fact that we have a right hand side term which will not be equal to 0. So we will have certain influence from the right hand side term, which we will see in the next module. We can see that already in this particular case, where we can define the value of dx and dy accordingly. So if we choose, if we want the number of spatial discretization to be in particular manner, for example, if we choose instead of 60, 6 points on the x and y direction, we will see the influence of the problem resolution will change accordingly. Let us run this code. Initially we had 60 and now we have changed it into 6, and if we run the same program and we are giving the boundary conditions to be 10, 0 and 0 on other sides, and if we run it, you will see the result is going to be categorically different in terms of quality. You see that the equipotential lines are not really symmetrical. There is going to be some influence in certain directions, and if you keep this one aside and I am going to run the same program with higher number of discretization, let us say I am going to increase it with 600. So I am going to run the same code. So what we can see here is, compared to the earlier problem where we had only 60 steps in the x and y direction, now we have increased the number of steps to 10 times more, and we can see the result is much more finer. So the resolution of the result is better compared to the previous simulation. So what we are trying to illustrate here is there is going to be an impact of the spatial and temporal discretization, and also the number of iteration that you are going to run on the top of the differencing method scheme itself. So there is going to be an impact of the differencing method, and on the top of the impact of the differencing method, the simulation parameters that we are going to use will influence the resolution or the quality of your solution. So that is a classical example for you to try. So we want you to use this particular code and try it for yourself, how the central differencing scheme is implemented in Matlab for Poisson on Laplace equation. In this case we have used for Laplace equation. We will try doing the same problem also in the case of Poisson equation to see how the right hand side can be implemented in Matlab, and I would like you to see how you can manipulate the spatial discretization in the x and y direction, and also the number of iteration that we are going to use. So that way you get a holistic understanding not only about the discretization method, not only about the differencing method, but also about the simulation parameter and its influence on the numerical result. So with that being said, I think we will stop here and we will come back in the next example and look at Poisson equation. Thank you.